Let's start with a simple question, the kind that usually precedes a trip to the emergency room or a closed casket funeral. What happens if you take a standard cup of coffee, remove all the boring, life-sustaining water, and replace it entirely with pure caffeine molecules? I don't mean a very strong espresso. I don't mean a red eye. I mean a standard mug where every single molecule inside is C8H10N4O2. The short answer, you take a sip. You vibrate at a frequency usually reserved for quartz crystals. And then you spontaneously into a cloud of chemical energy and regret. But, as a physicist, I am obligated to tell you that the short answer is boring. The long answer involves thermodynamics, neurochemistry, and a very bad day for our test subject, who we shall call Bob. Bob likes coffee. Bob is about to make a mistake. To understand the magnitude of this mistake, we have to look at what coffee actually is. In a normal, non-lethal universe, a cup of coffee is 99% water. Water is great. It has a high specific heat capacity, it dissolves things nicely, and it stops your blood from turning into sludge. Floating in that water is a tiny dusting of caffeine, about 100 milligrams for a standard cup. 100 milligrams. That's it. That is enough to block the "I'm tired" receptors in your brain and convince you that answering emails is a valid use of your limited time on Earth. Now let's play God with the variables. We take Bob's 2 to 40 milliliter mug. We banish the water. We fill that volume with pure caffeine. Here is our first problem. Physics doesn't like it when you try to drink solids. At room temperature, pure caffeine is a white, bitter powder. If Bob tries to drink this, he's just inhaling dust. He'll cough, choke, and look like he's trying to eat a bag of flour. It's embarrassing, but survivable. So, to make this a beverage, we have to respect the phase diagram. We need liquid caffeine. Caffeine doesn't melt until it hits 235 degrees Celsius. That is 455 degrees Fahrenheit. For context, water boils at 100 Celsius. Deep frying oil is usually around 180. We are talking about a cup of liquid that is significantly hotter than molten lead solder. So, before the chemistry even gets a chance to kill Bob, the thermodynamics will have a go. Bob lifts the mug. The ceramic is likely cracking because of the thermal shock, but Bob is committed. He tilts the cup. The moment this white-hot sludge touches his lips, we get the Leidenfrost effect's evil twin. The liquid caffeine has a high viscosity and a high heat capacity. It doesn't just burn, it cauterizes. It melts the tongue, the esophagus, and likely fuses the epiglottis shut. The structural integrity of Bob's face is now compromised. But let's assume Bob is indestructible. Let's assume Bob has a throat lined with the same tiles used on the space shuttle. Bob manages to swallow the entire cup. Now we have to do the math on the dosage. Density is key here. The density of water is 1 gram per milliliter. The density of caffeine is about 1.23 grams per milliliter. So, our 240 milliliter cup contains roughly 295 grams of pure caffeine. Not milligrams, grams. To put this in perspective, let's talk about the LD50. In toxicology, the LD50 is the lethal dose for 50% of the population. It's the amount of a substance required to kill half of the test subjects, usually mice, but in this case, stick figures. It is a grim statistical cliff. For an average human, the lethal dose of caffeine is estimated to be around 150 to 200 milligrams per kilogram of body weight. Let's say Bob is a healthy 70 kilograms. 70 kilogram times 150 milligrams per kilogram equals 10,500 milligrams. That is 10.5 grams. 10.5 grams is the U-die line. Bob just swallowed 295 grams. Bob has just consumed nearly 28 times the lethal dose. He hasn't just stepped over the line, he has strapped himself to a rocket and fired himself over the horizon of toxicity. So, what happens biologically? Caffeine works by antagonizing adenosine receptors. Adenosine is a chemical your body produces throughout the day. It floats around, finds its receptors in the brain, and slots in like a key. When the key turns, the brain says, "Okay, time to sleep." Caffeine is a master of disguise. It looks just like adenosine. It jams itself into the keyhole, but it doesn't turn. It just sits there, blocking the real adenosine from getting in. It's like putting superglue in the lock of your house. You can't get in to go to sleep. With 100 milligrams, you feel alert. With 295 grams, Bob isn't just alert. Bob is experiencing every nanosecond of existence simultaneously. Within minutes, the caffeine absorbs into the bloodstream. It hits the central nervous system like a freight train made of lightning. First, the tremors. We aren't talking about a jittery hand. We are talking about macro-scale vibration. His muscles begin to contract and release so rapidly that he might actually blur to the naked eye. This is tetany, sustained involuntary muscle contraction. Bob is essentially doing a full body plank, but at 60 hertz. Then, the heart. Your heart relies on a very specific electrical signal to pump blood. Tick-tock, tick-tock. Caffeine increases the heart rate. At this dose, the signal doesn't just speed up, it becomes white noise. The heart enters ventricular fibrillation. It's not pumping anymore, it's just quivering like a bag of angry worms. Blood pressure skyrockets. Capillaries in the eyes burst. Bob is crying blood, which is metal, but medically inadvisable. But here is the truly dark part, the brain. Caffeine is a stimulant. It lowers the threshold for neurons to fire. With this much stimulant, the threshold is gone. Every neuron in Bob's brain fires at once. This is the grand mal of grand mal seizures. It is a chaotic electrical storm. Bob is currently the most awake person who has ever lived. He is perceiving colors that don't exist. He can probably hear the background radiation of the universe for about 4 seconds, because then we have to talk about the energy, and this is where we get to the scientific deep dive. We usually think of calories as the thing that makes us fat. But in physics, a calorie C is just a unit of energy, specifically the energy needed to heat 1 kilogram of water by 1 degree Celsius. Caffeine is a hydrocarbon. It contains carbon, hydrogen, nitrogen, and oxygen. It burns. Literally, you can set caffeine powder on fire. The heat of combustion for caffeine is roughly 4,200 kilocalories per kilogram. Bob just drank 0.295 kilograms. 0.295 kilograms times 4,200 kilocalories per kilogram equals 1,239 kilocalories. That sounds manageable, right? That's like a large burger meal. But here is the difference: you digest a burger over 6 hours. The chemical energy is released slowly, controlled by enzymes stored as ATP or dissipated as waste heat over a long afternoon. However, with this level of toxicity, Bob's metabolism has been deregulated to the point of insanity. His cells are trying to process this influx, his muscles are spasming, creating friction and heat, and his autonomic nervous system is flooring the gas pedal on thermogenesis. He is generating heat faster than his body can radiate it away. Water has a high specific heat, which keeps us cool. But remember, we didn't drink water. We drank molten caffeine. Bob is starting at a core temperature that is already lethal. The chemical energy release coupled with the initial thermal shock creates a runaway feedback loop. The proteins in Bob's cells begin to denature. This is the scientific term for cooking. Like an egg white turning solid in a pan, Bob's internal organs are poaching themselves in their own juices. So, let's look at the visual hook again. The vibration, the combustion. Is it scientifically accurate to say it would explode? In the Michael Bay sense, no. There isn't enough oxidizer in his stomach to create a shockwave, but in the steam boiler failure sense, absolutely. As Bob's internal temperature spikes past 100 degrees Celsius, the water that actually makes up his body, the blood, the lymph, the cytoplasm flashes into steam. Water expands 1/600 times in volume when it turns to steam. Bob's skin, which is surprisingly tough, will hold for a moment. He will puff up like a disturbed pufferfish. And then, structural failure. The steam pressure overcomes the tensile strength of the dermis. Bob effectively ruptures. The release of high-pressure steam, mixed with the fine mist of biological fluids and the remaining molten caffeine, would create a rapidly expanding cloud of hot gas. To an outside observer, Bob takes a sip, vibrates violently as his nervous system shorts out, glows red as his internal temperature skyrockets, and then disappears in a puff of pink mist. It is a very inefficient way to get your morning energy boost. But wait, it could be worse. We assume standard chemical burning. If we really want to ruin the neighborhood, we could look at the mass energy equivalence, E equals mc squared. If we converted that 295 grams of caffeine entirely into pure energy, assuming Bob is some kind of antimatter reactor, we are talking about 26.5 petajoules of energy. That is roughly a 6 megaton nuclear detonation. That's not a cup of coffee. That is a city eraser. Bob takes a sip and the entire state of Delaware ceases to exist. Luckily, biology doesn't do nuclear fusion yet. So, let's dial it back to reality. The cup of pure caffeine is a bad idea. It is a thermal grenade, a neurotoxin nightmare, and a metabolic disaster. If you are tired, drink water, sleep more, or stick to the 100 milligrams in a standard cup. Because while physics is fun on paper, in practice, it really, really hurts. Don't be like Bob. Bob is now a stain on the carpet and a cautionary tale in a toxicology textbook. Drink responsible amounts of coffee, and leave the phase-changing, receptor-destroying, steam-exploding experiments to the cartoons. Thanks for watching. Now, go get some sleep. You look tired.